Good afternoon and welcome to our webinar on automating your BIM model validation today. We're grateful for you joining us and hope that you find the topics today insightful. I'm Paul Williams, one of the product managers here at Enable My Team, and we're fortunate enough to be joined by René Seeboth from DB Infrago. René, I'll let you introduce yourself.
Thank you, Paul. Hello, my name is René Seeboth. I am working for DB Infrago as a subject matter expert in BIM content management. I'm currently working in a central business unit for the stations where our team is focusing on standardization and digitization of our station design using BIM methodology.
Thanks again, René, for presenting with me today. Now, before we dive in, just a note to say that if you have any questions during the webinar, please drop them into the chat where we'll aim to answer them as we go along. Otherwise, we'll respond soon after. We'll also set aside 5 minutes at the end for any further questions. So to begin with, a brief introduction as to who Enable My Team are, for those who may not already know. We're an engineering technology company. We work to provide digital solutions to clients, focusing in the areas of asset information management, geospatial and BIM data, process automation and AI. Our product is our Atlas platform through which we deliver our solutions. Currently, we are working on infrastructure projects both here in the UK and further afield. René, over to you for a brief introduction of Deutsche Bahn and the work that you focus on there.
I will shortly introduce my company with some key facts. DB Infrago, as part of the DB group, is subdivided into 5 divisions, and stations is one of them. We operate 5,400 train stations and 700 station buildings. If we take a look at the other numbers, this means 9,300 platforms and around 2,700 elevators as an example. As you have seen by the numbers on the previous slide, this means we operate major train stations, but mainly simple train stations. Smaller stations mostly just consist of platforms, as you can see on the right side here. All in all, we can say that around 80% of our projects are small train stops.
Thanks, René. So our collaboration began back in 2023, following our successful POC in automating model checks alongside Deutsche Bahn. Since then, we have continued our work together to bring the proven concepts to life as fully fledged automations within Atlas. Okay, so a bit about our Atlas platform and the topics we'll be covering today. Atlas is an online browser-based collaborative GIS and BIM environment, which provides the means for building digital twins, consisting of a multi-level data federation and management platform. At its foundation is an asset information management system, where asset configuration baselines, consisting of your core data requirements, can be created and managed in line with company, customer, and project data requirements. On top of this sits a feature-rich GIS and 3D viewer, where GIS layers, point cloud, and 3D model data can be added and federated, forming a complete picture for concurrent viewing and interaction within the platform. As we believe in open data and interoperability, integration with Atlas is possible via its Open REST API, meaning your data within Atlas can be accessed and updated via workflow integrations that you may want to configure. The API also provides the means to produce data reporting at any level of detail. So today we'll be taking a dive into our automated model checking workflows that have been developed in close collaboration with René and his team. In each case, René will be providing some background as to why they needed to bring about automated verification for their design models, and we'll run through level of information checks, which involve the verification of data held within the model against each element. Custom technical rule checks. These act to verify models against company, client, or project requirements. And finally, level of geometry checks, which verify the geometry of model elements against a predefined object library of template models. Starting with level of information checks, I'll hand over to René to explain why Deutsche Bahn are looking to automate such checks. Then I'll explain our solution and a bit about how it works.
Currently, we regularly receive models that don't fulfill our information requirements, and because of this, we have a large undertaking of manually verifying each model we receive. Common issues being missing attributes, wrong data formats, p-sets, syntax, etc. All in all, some models are poor in information quality. Currently, for most of our projects, we are not doing a complete LOI check. We are only doing proportional checks, which are in themselves time-consuming and means that some errors will always remain uncaptured. Also, due to the human factor, these checks are naturally error-prone. The reporting process is also not yet a standardized process, which is used throughout all our projects. Several software solutions can be used for reporting issues. In some projects, BCF is used to communicate issues, but in some others, it's just PDF. This also means we could have a lag in communication.
Thanks, René. So regarding the challenges expressed, as with all the checks we're covering today, it's obvious that automation is the way forward. However, for the level of information checking, which, as the name suggests, relies on the data structure, there are some prerequisites that need to be in place prior to being able to complete such a check. Therefore, to be able to run these checks in Atlas, there needs to be an asset configuration defined. And the model attribute that holds the classification of the model elements needs to be specified, as this is key to identifying which class from the asset configuration an element corresponds to, and therefore what data requirements that need to be met. This being the case, it highlights the importance of information and BIM model requirements being implemented consistently for a company or a project. Without this, model data will risk being inconsistent and the inability to get the most out of these checks, as they will fail at the first hurdle, i.e. the model elements can't be matched to any class within the configuration. With the prerequisites in place, we move on to the workflow. Here's a high-level diagram of the check stages. Firstly, the attempt to identify the classification of the model element takes place. This is why we need to define the model attribute expected to contain the classification. Once the classification is known, does it match a class within the asset configuration? With this being successful, the specific class attribute requirements can be verified. As you can see, there are different check failures that can occur depending on where in the workflow the check fails. We'll now take a look at how the check is triggered and viewing the results. The automated model check options appear within the model menu. On selecting LOI check, the pre-check dialog box opens, where the required criteria needs selecting. Firstly, the asset configuration to verify against, then the life cycle stage you wish to check. These stages are set against the attribution within the asset configuration and allow the check to focus on a specific life cycle stage. Running the check triggers notifications and a processing icon appears to inform users that the check is in progress. An estimated check duration is provided as an indication of when the results may become available. On completion of the check process, a completion notification is provided, both via email and within the platform. To review the results, again navigate to the model menu and select LOI check. The results table will open and display any check failures. The table offers the means to navigate and interrogate the check results. Results styling can be toggled on to provide a clearer view of failed elements within the model. Red for failures, green for passes, and yellow for overridden failures. Elements with no styling are those which are missing the prerequisite element classification attribute, so could not be checked, but these are still classed as failures within the table. Expanding the table rows gives visibility to each individual failure reason. The table is also dynamically filtered by the selections made within the model view. Therefore, to quickly view an element's failure result, you can simply select it. Here the table is filtered to the lift shaft asset, and I'm going to override the failures by manually approving them. Once overridden, you can see the styling update to yellow to indicate that the failure has been overridden. On the flip side, it's also possible to zoom to failed elements from within the table by clicking on the adjacent Zoom To button against the individual row. And we can also see that it's possible to manually override failures in bulk. By filtering the table to a specific criteria and then using the Approve Filtered option, you can assign a new failure override reason, and this will be held against each individual failed element that was within the filter. And again, the styling of these elements are then updated. Finally, if you need to export and share the results, this can be achieved by exporting the results within a BCF report, which can then be viewed in alternative applications. So with reference to the initial problem statements, you can see that all bases are now covered to provide full automated checks that deliver consistent standardized outputs that can be easily assessed and addressed. Next up, we have the custom checks. And again, Rani will start by explaining the initial problem statement.
We have a huge number of mandatory design requirements that need to be considered during the planning process. Those requirements are sometimes not easy to interpret because they can contain many cross-references and appendices. Right now, models and also 2D drawings are checked manually. The fact that we are still checking 2D drawings manually leads back to the fact that some inspectors are not yet trained to check 3D models. These manual checks are also, again, very error-prone.
So to address this challenge, we have developed a means of configuring rule sets that do not require any prerequisites and therefore can be utilized without any asset configuration being held. Having this ability is a powerful tool should you need flexibility to configure checks that are specific to either your company, your client, or your project. Whilst the rules will be configured by an admin user, they can be utilized by any user of the project. There are two main categories of rules: single asset class checks and class-to-class checks. The single class checks cover information checks similar to the LOI checks we just discussed, geometry checks, area checks, for example, checking a modeled asset covers the required area, i.e. if a danger zone is modeled, and a gradient checks to confirm that required gradients are modeled against the model elements. Whilst class-to-class checks cover eventualities where you may want to check proximities between two or more classes, whether this be linear, straight line distances, or planar, which check proximities between classes in all directions of a given plane. Again, we'll now take a look at a complete run-through, from setting up a rule to reviewing the results. Requirements are configured as rule sets, where one or more rules can be created under the set and work in conjunction to determine whether the overall requirement is met within the model or not. First, the rule set is created by adding its name and description. Tags can also be assigned. These give users the option to filter which rule sets to run when running the checks against the model. Here I'm setting up an example where we'll be checking that the end of the platform perimeter railings are the correct distance from the tracks. Once the set is created, individual rules can be added. A rule name and description are added, and for the individual rules there's an option to upload supporting documentation or an image. This is useful to support a user's understanding of exactly what the check is trying to achieve. Once these 3 bits of information are populated, then the check type for the rule can be selected. For this example, we're going to be using class to class. As previously mentioned, custom checks can be configured without the need for an asset configuration. But for either check type, it is still necessary to define the conditions by which an element class is determined from the model. This can be as simple as specifying that when a specific attribute equals a specific value, or can be more complex by involving multiple attributes and their values to determine the class of an element. This flexibility plays advantage, for example, if you wanted to set up checks to only involve model elements of a certain status or location. Once the class definitions are provided, the next stage is to set up the conditions of the check. Here I'm setting up a planar check that will check the closest points of the railings to the tracks, making sure that they're a distance equal to or greater than 2.5 meters. If the distance is not achieved, then the specific railing will be reported as a failure. When all the rules for a rule set have been configured, the set can then be used against models. The configured rules are created against the JSON schema, and this can also be viewed. I'll also mention a roadmap development involving this JSON schema later on. Moving on to running the checks. Again, from within the Models menu, the option of Run Custom Checks can be selected, which is under Model Rules. This will open a dialog window where users will select which rule sets they wish to run against the model. Within the Rule Set Selection dialog window, you can choose which rules you wish to set for the model. The dialog also offers the chance to view the rule sets that exist. This includes any supporting images or documentation that may have been uploaded during the rule setup. And again, upon triggering the run, you will be provided with a notification. On to the results. When viewing the results of the custom checks, the table displays all model elements that were involved in the checks under a Class A asset, specifying whether the element passed or failed for each check it was involved in. Where a check allows for a visualization, such as showing the measurement between a Class A and Class B element, there is a visualization button. This will open a new visualization window which displays a 2D layout depicting the measurement taken during the rule check. This is so that users can verify the result and, if necessary, update the rule if measurements are not in the correct axis or plane as intended. Also to mention, in addition to automated rule checks, these custom rules allow for manual check rules to be defined. Rules that can't be automated because certain aspects aren't explicitly modelled. For example, ensuring there is manoeuvrability space for wheelchair users on a platform. The manual checks will still be associated with a class definition and will be reported as failures by default within the results. Their inclusion within the results table both informs users that the manual check is required and allows them to undertake the check within Atlas and subsequently mark the result as a pass or leave it as a failure to be resolved. Being able to configure custom model checks brings a new dimension to the capabilities of Atlas and gives you the facility to build checks in line with company, client or project requirements. And once in place, they are available for repeat use wherever necessary and can form part of your BIM verification workflows. Lastly, we'll move on to the level of geometry checks. Back over to you, René, for the introduction.
At DB Infrago, within the stations team, we hold a standardized 3D object library that are provided to all our planners. These standardized objects are based on construction standards by our department. These standards provide information on the geometry of the objects. Using DB construction standards in our project is mandatory. Therefore, the geometry of 3D objects is also precisely described. Right now, inspectors have to manually check if the objects that are used inside an overall 3D design model are matching the current requirements. The checks can only be done as a proportional check, and even so, it's not always easy to visualize differences in geometry by just comparing the 3D library objects with the instances of the corresponding element in the model. And taking numerous measurements for each element is just not practical.
LOG checks compare the geometry of each model element against a pre-configured geometry template. Again, there are a couple of prerequisites for this check. One, there needs to be an asset configuration in place. And secondly, within the asset configuration, model template files need to be uploaded. To be able to match a model element to a template model, the model's element's object name property must match the name of the template. Upon a match being found, the two sets of geometry are compared to identify any discrepancies in dimensions and geometry features. Running the check is similar to other checks, with only the asset configuration against which the templates are held needing selecting. The results table only contains check failures, and where a failure relates to a geometry mismatch between the model element and its match template, a visualization is available. The visualization highlights the geometry in three ways. Red, non-valid asset mesh, indicates where model element geometry is additional to what is held in the template. Orange, non-valid template mesh, indicates where the model element is missing geometry that exists within the template. And green, valid mesh, indicates where the model element and template align. For the model geometry checks, the automation we have introduced provides the means to check entire models efficiently and highlight discrepancies to the user in a consolidated fashion along with supporting visualizations. Atlas can also verify parametric elements, provided that the parametric templates are provided. So to sum up these verification features, Atlas now provides you with the tool to become more efficient in your BIM model verification and deliver your projects more confidently, moving away from manual processes into more reliable and flexible automation. I'll hand you back to Rene now, just so he can wrap up on his conclusion of the project work and our successful collaboration together.
Finally, let me briefly summarize the project. Overall, the collaboration with EMT worked very well. We followed an agile approach, which helped us stay flexible when requirements were still evolving. This allowed us to improve things step by step. Together, we worked closely to define and improve the model quality requirements. Our partner EMT did a great job fulfilling these requirements. In some cases, the requirements were not immediately clear, but we clarified them together through discussions. To support this, we used mockups and click dummies, which made things easier to understand. In the end, this strong collaboration helped us achieve very good results. Thank you, EMT, for the opportunity to join this webinar and for your focused work on this project. I hope these features provide a wider benefit to our audience.
Thanks again, Rene. I think you summed it up nicely there on the delivery of these developments. But we're not stopping the development of these features. We intend to continue improving them and incorporating more advanced features as we move forward. Key roadmap items to note, particularly with regard to the most flexible and powerful check option in the custom checks. We have a few enhancements that we are working towards. Firstly, allowing rules to be configured outside of Atlas using the JSON schema format previously mentioned, allowing them to be imported for use. This will make the setup of these rules more efficient and open. And then via the use of the Atlas Intelligence chatbot, allowing automated rule creation through descriptive prompts. And finally, defining and running bespoke rules directly through the chatbot itself. And that brings us to the end of our webinar today. I'd like to thank Rene once again for sharing his input and to you all for attending. We hope that this has got you thinking as to how such features could benefit you and your teams in the verification and assurance of your BIM models. If you have any questions you wish to ask, please do so via the Q&A section, and if we can, we'll answer them right away, otherwise shortly after the webinar finishes.